Thanks, everybody. Thanks. I've been fortunate enough to work on a number of graphite and lithium projects now with great clients, client representatives, and a great team at IMO, Metallurgy Proprietary Limited, and also Metallurgy's part owners, along with IMO, Strategic Metallurgy. Oops, sorry guys. The properties of the graphite flake itself is imperative into achieving a high-grade concentrate. I've learnt if the graphite has gangue entrained within the flake, it is going to be more difficult to achieve a high grade. I characterise a high grade as greater than 96% final carbon content. I think flake content has already been well characterised today. To upgrade the graphite, an initial crush and grind of the rock is required to liberate the graphite from the gangue minerals, which most of you will be aware is the initial process for just about all ore processing. When I first started in the graphite game, based on the fact that the graphite smears and some of its uses, I didn't think it was hard. But after my technicians told me this concentrate just won't pulverise, and I found it had a nominal bond mill work index of 48 kilowatt hours per tonne, then my opinion changed. In this slide you can see the bond mill work indices of other minerals, and most of us during our lives would have had the misfortune of getting sand primarily made of quartz in our mouths and trying to break the sand with our teeth, which is not easy. So whilst graphite is hard, like all minerals, it will break if too much energy is imparted on it. In this picture you can see discrete graphite and gangue layers, which will act as cleavage planes, which should allow the graphite to liberate from the gangue during the initial crush and grind process. The gangue mineral hardness has an effect on maintaining flake size. If the flake is surrounded by hard gangue minerals versus, for example, a clay, then more energy is required to liberate the flake from the graphite, and it will be more difficult to maintain the flake content. Sorry, that's gangue from the graphite. The comminution techniques employed are, however, aimed to break the flake and not the actual flake. If there is gangue within the flake, then it becomes more difficult to maintain the flake distribution and achieve a high-grade concentrate. Once the gangue is removed from the flake edges and the final flake concentrate is recovered, it's then the flake to gangue ratio which will ultimately determine the graphite grade. The flake can be upgraded, however it's then via dissolution of the gangue within the flake and often with a combination of caustic and acids. This then makes the process expensive and often not economical. Most of you will be aware that a graphite particle is made up of graphene layers stacked on top of each other, and that graphene is defined as a single layer of graphite. If there is gangue between the graphene layers within a graphite particle, then liberating that particle is the only way to liberate the gangue from the graphite particle, as the caustic and acids won't be able to diffuse through the graphene layers to remove the gangue within those graphite particles. Flotation of graphite is the traditional method used to upgrade graphite, and ultimately it's the only way to determine the final flake content and grade of a graphite sample. Characterising the sample by either a size by assay on the feed or using various petrology techniques such as SEM are a good indicator, but it will not give you the final answer. Graphite itself is naturally hydrophobic, meaning it does not like water, but it still needs a little help in terms of recovery. Oxide flotation, which graphite is characterised into, is often difficult as the collectors used will attach to and recover some of the gangue minerals. But with graphite, it's fortunate that the collectors used will generally only attach to the graphite, enabling a high-grade concentrate at excellent recoveries to often be achieved, again providing the graphite is liberated. Typically kerosene or other fuel oils are used which are non-ionic collectors, meaning they have no charge. It selectively coats the graphite particle, which are then rendered hydrophobic, and quite often you'll see the graphite float to the surface of the cell as a nice grey slick as shown in this video. There are some naturally hydrophobic graphite minerals already on the surface of the slurry, which initially disperses upon addition of the collector. As the collector mixes through the slurry, which is known as conditioning, you'll start to see the graphite concentrate on the surface of the slurry. Most of you will at some stage mixed a fuel oil with water and seen the fuel oil float to the top of the water as a slick, which is essentially what's happening here. Some of you may have seen firsthand or various company releases a form of graphite flotation during the drilling process, where graphite is flowing out of the rig with contact from the drilling oil or water with the liberated graphite flake. The graphite, however, still requires a bubble to attach to it, which then requires a frothing agent to be added, similar to detergent, so that a stable froth which the graphite can concentrate into can be generated and ultimately collected as shown in this video. The video commences at the end of the conditioning stage, which is generally ranges from 2 to 5 minutes, and you can see there is more graphite on the surface of the slurry. As we slowly add air, the graphite begins to form a froth bed, which continues to rise to the top of the cell as the airflow rate is increased. If you look carefully within the froth, you'll see fine gangue, which is physically entrained within the froth and ultimately needs to be removed during further cleaning. As I mentioned before, graphite flotation is selective, but ultimately it requires multiple stages, as gangue minerals will still come along for the ride through physical entrainment of the froth as seen in the previous slide. Physical entrainment is when gangue particles inadvertently enter the froth, physically become stuck there and are collected into the concentrate. Gangue is also recovered into the froth when physically attached to graphite minerals. The beneficiation flow sheet is generally broken up into multiple stages of flotation and regrinding in order to achieve a final concentrate. The initial flotation stage is termed the rougher stage. The subsequent regrind stages are numbered to clarify their position in the flow sheet. The flotation stage after the regrind is termed the regrind flotation stage, and the stages after the final regrind stage are termed the cleaner stage. This flow sheet is a good starting point for a rougher regrind cleaner test, which at IMO we've been able to generate first time a greater than 96% total graphitic carbon concentrate for a number of samples now, and even a greater than 98% total graphitic carbon concentrate on certain well-liberated samples. I'll go into more detail in the next slide why we have multiple cleaning stages after the regrind stage 3 and only a single stage after regrind stage 1 and 2. The regrind stages are what I've found to be most important in achieving a high-grade concentrate with good flake distribution. The picture on the left shows a typical mill which lifts the media, generally either rods or balls, and drops them onto the ore. However, this is not what we want, as it can reduce the amount of flake. What we do want is shown on the right side of the slide, which is to have the media essentially roll over the graphite particles and liberate the flake from the graphite flake edges, purifying the graphite. As I mentioned previously, having soft gangue minerals is advantageous in this stage, as less energy has to be applied to liberate the flake, reducing the chances of breaking the flake. You'll notice after the regrind stage there is only a single flotation stage, as the aim is to remove the majority of the gangue that has been liberated or come along for the ride in the previous flotation stage through physical entrainment before the regrind process gets repeated again. In this flow sheet I've used 3 regrind stages, but I've seen other flow sheets with more and less regrind stages. When scaling up this process, it's important to consider the size of the mill and media required. For if it's a traditional horizontal mill, a lower than critical speed and ultimately energy input is required. The mill on the left would typically run at about 70 to 75% critical speed, whilst the mill on the right may be down to only 20 to 25% critical speed. The final cleaner flotation stages utilise multiple stages of flotation with the aim of rejecting all the gangue minerals. Typically the coarse flake fraction will only incrementally increase in grade. However, the fine, particularly the minus 75 micron fraction, are where the real increases in grade are achieved, and I've seen it increase from less than 80% to greater than 96% total graphitic carbon. The scale up of the flotation can also be quite difficult, as a scale up factor of typically of 2 to 3 is required for sulfide and oxide minerals, whilst graphite can require a scale up factor of 3 to 5 times. Ultimately, the only way to determine this scale up factor for each individual ore is by piloting or having a process engineering team with significant graphite processing experience. Once the final concentrate is produced, it's then typically sized to determine the flake distribution, and then each individual size fraction is assayed to determine the graphite content. I've shown an example from a Cabaran release from 15th of June 2015 as an example of the final flotation concentrate. I must stress that this result was achieved after a significant amount of test work trialling different flow sheets and conditions, and that the flow sheet I showed previously is not the final flow sheet selected for Cabaran. You'll notice that the grades quoted in the Cabaran release are from a single LOI or loss on ignition analysis. It is acceptable to use LOI measurements for graphite content within concentrates. All that should remain in the final concentrate is graphite and the gangue metal oxides either adhering to or within the graphite matrix, which shouldn't volatilise. We'll still typically get LECO measurements conducted on the concentrate to confirm the LOI measurements, though typically they are lower than the LOI measurements, but I generally expect by less than 1% or 2%. Whilst talking to different companies will result in different answers on graphite product demand, IMO was engaged by Triton to conduct a marketing study and determine product testing requirements for graphite products. This resulted in the primary demand being for steel and refractories. Feedback we received from attendees at the most recent London Graphite Conference is that graphite use in the recarburizing market is essentially non-existent due to the price of high-grade graphite being overpriced compared to other suitable available carbon products. Most of the current excitement we see in the graphite market is confined to the expected increases in graphite consumption in lithium-ion batteries, spherical and expandable graphite. It is interesting that a lot of company classification is based around the final concentrate flake distribution. However, the most hype growth in the industry for graphite, the lithium-ion battery market, requires fine graphite, albeit spheroidized in either a jet or planetary mill. IMO's research has led us to conclude that jet milling is really the only option to commercially produce spherical graphite, and during that process, approximately 40 to 50% reports to spherical graphite. The discussions I've had with my clients have indicated that it's the lack of flake being supplied from China, balanced with flake demand, is the real reason for the higher jumbo flake compared to finer flake prices. The list of battery and expandable graphite tests are quite extensive, and it's often the research institutes who have the capabilities to complete this test. Of note is the Talga announcement on the 17th of February, where it appears they've bypassed a lot of this testing and gone straight to determining the discharge capacity of their graphite, which is in line with commercial lithium-ion battery standards. You'll see the properties of both spherical and expandable graphite pasted on this slide, along with some XRD pictures of unexpanded flake graphite, which looks to be a final beneficiation concentrate, and pictures of expanded graphite. The process of producing expanded graphite is from the intercalation of appropriately sized ions, such as a sulfate ion, which can fit between the graphite layers, and then when rapidly heated, undergoes exponential expansion to produce expanded graphite. The expansion potential of graphite flake is primarily dependent on the number of graphene layers or stack height of the flake. Our research indicates that this is another growth market for in particular, flake graphite. IMO have developed procedures which can determine graphite flake expansion potential. Now onto the lithium section. Spodumene is the primary mineral primarily responsible for share portfolio increases of those in the room lucky enough to see the bubble forming. Spodumene itself is a lithium alumina inner silicate. The most important gangue mineral shown in this slide is mica, and the reason for it being the most important gangue mineral is that it can contain lithium. This needs to be taken into account from drill results, as assays will inform investors of the lithium content, but not the lithium mineral association. If the mineral characterisation and test work is not done properly up front, operators may not potentially achieve their recovery targets. Spodumene is typically coarsely liberated, enabling producers and budding explorers to produce a coarse high-grade product from a relatively coarse upfront gravity circuit, which exploits the specific gravity difference, which generally ranges from 0.4 to 0.6 metres cubed per tonne between the spodumene and the gangue minerals. Whilst the gravity circuit will produce a coarse, relatively pure spodumene product and rejects fraction with minimal spodumene and primarily gangue minerals, it will also produce a middlings fraction, which consists of lower grade spodumene and gangue mineral composites, which require further downstream processing by grinding, gravity, flotation, and magnetic separation. This slide shows the Pilgangoora process flowsheet taken from the Pilbara Minerals pre-feasibility study released on the 16th of March. I'd like to thank Pilbara Minerals for allowing me to use this flowsheet in my presentation, along with the opportunity to work on their ore through IMO's joint-owned test work facility, Metallurgical. The flowsheet consists of an upfront primary and secondary crushing and screening facility, shown here. The crushed material is then ground using a high pressure grind rolls, which is used to liberate the coarsely liberated spodumene from the gangue minerals. Anybody who's worked with these pegmatites will know just how hard and abrasive they can be, so it's understandable why Pilbara have selected this comminution style of circuit. I've been lucky enough to see just how hard this material is firsthand, watching the metallurgy technicians cut core from a lithium pegmatite deposit. The task has been very laborious for the guys, and they've had to employ specialist blades, as the normal cutting blades were lasting less than half a day and cutting at less than half the rate. The style of upfront comminution circuit, however, is popular amongst the lithium explorers / producers, with others employing a similar style of circuit. However, there has been a healthy discussion amongst metallurgists that a HPGR has the potential to produce more fines, so it will be interesting once data comes out from these operations to see if this is the case. The rolls, however, are adjustable, so setting the gap to minimise the recirculating load and fines produced will be the challenge. Greenbushes, who have been producing prior to the turn of the century, have employed a more traditional style of circuit, which consists of a 4-stage crush circuit, though due to the wear exhibited in particularly on the 3rd and 4th crushing stages, this circuit can be troublesome, resulting in significant downtime. At IMO, we believe there could be some possible merits for a 3-stage crushing circuit with a rod mill finish, as the rods act as a screen to prevent overproduction of fines. Rod mills seem to have gone out of fashion as plant capacity increased, resulting in more SAG mills, though we still believe they do have a purpose, and so does the Northern Hemisphere, who extensively use rod mills in a number of applications. The previously discussed gravity circuit, popularly employed, is a heavy meteor cyclone. Oops, how do I go back? All right, cool, thanks. The heavy meteor stage can only process material above a certain size fraction, typically greater than 0.5 millimetres, hence material finer than 0.5 millimetres will report to the fines processing circuit. You can see 3 stages of heavy meteor separation on the flow sheet, with the first run at the lowest SG to separate the liberated gangue from both composite and liberated spodumene. The cyclone overflow, also known as the floats or light fraction from this stage, which contains the liberated gangue, is rejected to tails, whilst the underflow, also known as the sinks or heavies, proceeds to the 2nd stage of cycloning. With the liberated gangue now removed, the aim is to separate the spodumene and gangue composites, or previously described as the middlings fraction, from the liberated coarse spodumene. The final heavy meteor stage includes separation of a previously not mentioned mineral from the liberated spodumene, which is tantalite, a byproduct of this process, and most importantly, another revenue stream. The composite spodumene and gangue particles, or middling stream from the heavy meteor cyclone, reports to the grinding circuit, which aims at liberating the associated spodumene and gangue minerals from each other so that they can be further separated downstream. The liberated stream is combined with the undersized material generated from the HPGR prior to undergoing gravity separation, which separates the finer tantalite, which reports to this secondary revenue stream down the bottom there. The material is thickened prior to then undergoing a gangue pre-flotation stage, which we've assumed that the HM stands for heavy minerals, and again assumed that it's separating other heavy minerals such as garnet, which we've seen associated with pegmatites. The flotation process typically consists of a series of rougher cells whose aim is to maximise spodumene recovery. However, it will also take gangue minerals along for the ride. Unlike graphite flotation and also sulfide mineral flotation, which tends to be more selective, lithium flotation falls into the category of oxide flotation, which tends to have a higher degree of gangue entrainment. It doesn't mean that the separation overall is less effective. It just means that the mass recovery during the rougher stage can be higher. The process generally takes longer to develop, and the circuit configuration and reagent blend employed requires more test work to develop as well. The rougher stage then undergoes multiple cleaner flotation stages similar to graphite. However, there are no regrinding stages in between the individual flotation stages to minimise slimes or ultrafines production, which for the majority of oxide flotation processes significantly foul the concentrate. The flotation product then undergoes a series of magnetic separation steps to remove any ion-bearing particles, which is a primary penalty element for the fine spodumene product. The test work required for developing a flow sheet of this type is extensive and costly, so it's just as well the lithium industry has been able to raise the funds they have. Can't imagine the drilling and then cutting such hard material would be cheap either. The initial test work required for the coarse spodumene characterisation is heavy liquid separation, test work in conjunction with mineralogy. Typically a sample is crushed to different crush sizes ranging from approximately 8 millimetres down to 1 millimetres. This crushed material is then sized into a range of size fractions with heavy liquid separation conducted using a range of different specific gravities on each size fraction. Mineralogy is also conducted on size fractions from generally the coarsest crush to narrow the range of crush sizes that require HLS test work. By doing the test work at different crush sizes, the amount of spodumene lost to the fines less than 0.5mm fraction, which is too fine for the heavy media separation work, can be determined, and the ideal size fraction which will achieve the highest portion of liberated spodumene. The trade-off that needs to be analysed is what size fraction does the coarse-grained spodumene liberate in conjunction with the amount of fines reporting to the fine spodumene circuit. The coarser the grind size, the less losses to the fines fraction. However, the amount of spodumene reporting to the middlings fraction and subsequently the fine circuit will increase. The finer the grind size, the higher the losses to the fines fraction. However, the amount of spodumene lost to the middlings fraction and subsequently the fine circuit decreases. In the end, the recovery of coarse spodumene at a saleable grade will win out. You'll notice the upfront test work utilises heavy liquid separation, whilst the overall process utilises heavy media separation. The metallurgist modelling the data needs to know how this is going to translate to a heavy media cyclone, and ultimately a heavy media piloting run will need to be conducted based on the heavy liquid separation data to confirm the model and provide extra data required for the scale up to a full process plant. This slide shows dense media cyclone modelling conducted by IMO on two size fractions, a coarse and fine size fraction. The model targets a lithium oxide or lithia grade of 6% at a low cumulative sinks mass, which is at the left-hand side of the graph. The greater the fine product, which is the top line, is higher, whilst at the lower sinks mass, the greater the fines product is lower. The higher lithia grade of the fines compared to the coarse at the reduced sinks mass is due to the increased liberation of the spodumene at the finer size, resulting in a more efficient separation and lower gangue mineral recoveries. The fines grade, however, dips here as spodumene recovery is higher up front, which is as we move down the graph, and gangue mineral liberation, which goes hand in hand with spodumene liberation, has increased. As the SG decreases and the sinks mass increases, liberated gangue minerals will report to the sinks. However, for the coarse fraction, these gangue minerals will contain spodumene, and therefore the lithia grade will ultimately be higher. As you can see, the lines cross over. At 100% recovery, we're back to the head grade. The downstream process isn't any less complicated and ultimately also requires confirmation from piloting, especially as the middlings fraction generated from the heavy media circuit isn't generally available until the DFS. This means that upfront testing conducted on commonly the minus 0.5mm fraction generated from whole ore material needs to be confirmed on a combined heavy media separation middlings and less than 0.5mm products. As I mentioned previously, oxide flotation is generally the most complex type of flotation. However, some of the multiple sulfide commodity ores do give it a good run for its money. I'm not going to go into too much detail into the intricacies of downstream flotation test work, whilst this slide details the steps generally undertaken for the flotation process development. Thank you very much.